Hello guys, welcome to Maths with EJD. Starting from this video, I'll be talking about basic calculus. I'll take us through some ideas, some concepts in calculus, and I hope it's going to be a very interesting journey. So let's get into it. In these videos, I'll be talking about these areas. I'll talk about the whole process of calculus, starting from functions of real variables, and then I'll move on to functions of real variables alone. Probably I'll have to break that into two videos. So I'll talk about about functions generally and operations on functions, and then we'll move on to limits and continuity of functions of real variables, probably broken into two videos depending on what it looks like. Then differentiation, applications of differentiation, integration, and application of integration. I know it's going to be a very nice time, so fasten your seatbelt and come along with me. Okay, so yes, let's go ahead and talk about functions of real variables. The definition of a function of a real variable, that's the first thing we'll look at. Then the next, we'll talk about types of functions of real variables and their graphs. Then, of course, in the second video after this one, we'll talk about operations on functions, which will be inversion of functions of real variables and composition of functions of real variables. And of course, as my practice is, you're going to find some exercise to play with. So let's go on to talk about the definition. So definition of a function of a real variable, it's very straightforward. A function is basically like a law, that holds every time. Once you establish the law, it will always hold that way. So a function is a relationship between two sets, right? You have two sets. It's a relationship between two sets in which each member of one set corresponds uniquely to a member of the other set. So you have two sets. I'm going to give you a practical example of this. So you have two sets, and there is a connection between the two sets. So the following symbols can be used to represent functions, maybe just f or f of x, and so on. Then, as a result of the other things associated to a function, we also need to know about variables, right? So the members of each set are referred to as variables. So you have two sets. In each set, you have what you call variables. And a set of variables whose values are determined by another set of variables are known as dependent variables. So there are some variables that are determined by another set of variables. But then those variables which determine them are known as independent variables. Generally speaking, when you say y equals f of x, when you say y equals f of x, what you're simply saying is that you have a set of variables called x. You have a set of variables called x, which end up determining what y would be. So in that case now, x will be your independent variables, your y, which depend on x, are your dependent variables. That's really important to understand. So that's basically the idea of a function. Okay. So I mean, to bring it to clarity, so you can look at this. Okay, this looks a bit faint, but here you have the independent variables, and here you have the dependent variables. For instance, I've chosen two sets, a practical set of boxing, golf, football, and kickboxing. So here we chose box. So what we are choosing that boxing is our independent variable, which determines the big players, right? So boxing is there, and then there are people who box, and then there are some champions. So now matching boxing with Tyson Fury, for instance, which is one of the boxing champions. Then golf mapped to Tiger Woods, football mapped to Lionel Messi, and then kickboxing mapped to Israel Adesanya, right? So in this case, now I'm taking the group of sports, the set of sports as the independent variable, which determine the champions, you know. So in this case now, so a function is more like an input and output kind of thing. So the independent variable can be regarded as inputs. So the independent variable is like the input, the sport is the inputs, and the outputs are the champions from that sport, right? So the function f of x is the system, while the dependent variable is the output. So the independent variable can be regarded as input. So you have an input. So you feed the input into a system, and then you get an output, you know. So that is the kind of thing a function is. Of course, you're still going to see this in real mathematical terms. So let's go to slide 6. Of course, variables can be numbers. Most of the times, we can consider variables to be numbers. So in this case, I just want to quickly run through classification of numbers, which I got from a site. So generally speaking, you have numbers, numbers, and numbers are, well, numbers can be broadly seen as complex, right? They are broadly seen as complex, but under complex, you can now have imaginary numbers and real numbers. When you talk about imaginary numbers, they are numbers that involve the square root of -1, where you now assign I or maybe J, depending on what you use in your own field. And then the real numbers are now numbers that are devoid of the complex numbers like this. So under real numbers now, so imaginary, that's how far it goes. We don't get to talk about it further. But of course, there's a branch of mathematics that studies the whole complex number thing. So maybe one of these is I'll also make videos on complex numbers. So under real now, you have rational numbers and you have irrational numbers. And a rational number, just like the word sounds, right? Just like the word comes across, it's a rational number, rational. So it means a function, like a number that can be expressed as the integer, as the ratio of two integers, sorry. And the irrational number cannot be expressed as the ratio of two integers. So you're going to see those examples. Under rational numbers, now you have integers. Integers are basically whole numbers, both positive and negative, including 0. And then you have negative integers like -1, -2, or onwards like that. And you have under integers, you have positive integers, which are generally known as natural numbers, and they are non-negative. So under that, you have whole numbers and all the rest. And then you have counting numbers like 1, 2, 3, 4, 5, 6, 7, and so on and so forth. So that's just a quick brush with the classification of numbers, because that's going to be useful as we move on. Okay, so let's go ahead as we consider what is real valued function. Since I've just told you about complex numbers and real numbers. So real valued functions, for a real valued function of a real variable is a function which maps a real number x, which belongs to the set of real numbers, to any real number y, which belongs to another real number. So don't forget where we're coming from. We said a function maps two sets together, just like we mapped a list of sports with the champions in those sports, or some champions in those sports, so to speak. So in this case now, so for a real value function, we are saying that we have a function f of x, which is like our system, right? Then you put x into it and you get y. So both x and y are real numbers. So in this case, we are talking about real valued functions, not complex valued functions, because there's a whole area dealing with all that. So let's take a practical example. For instance, students' performance in calculus can be considered as a function of the course lecturer's capacities to teach. The way a lecturer teaches may determine a student performance, right? So in that case, of course, there are many other things that determines a student performance, but let's just assume that in this case, you are considering that the input is the lecturer's capacity while the output is the student's performance. That's one thing. Of course, many other things can be considered. So in this case now, we can say here, student performance y is the dependent variable, while lecturer's capacity is x is the independent variable. So it means student performance depends on lecturer's capacities. So we can then represent the relationship as y equals f of x, right? So the next thing I like to talk about afterwards, it would now be different types of functions you're going to encounter in calculus, or generally in mathematics. So let's talk about types of functions of real variables and their graphs. So the first thing I'd like to talk about would be polynomial functions. So a polynomial function is a mathematical expression consisting of the sum of a number of terms, each of which is the product of a constant and a variable raised to a positive integral power. I mean, that's a lot of words right there. What we are simply saying is that for a polynomial function, this is the kind of thing you have. You have a number, you have a variable x raised to a particular whole number power, and you have other things either added or subtracted. That's what the whole story is about. So this is a very good example of a polynomial function. So poly means many, right? Poly means many. Nomial, nom there means terms. So many term function. So a term that has many terms. And the one particular thing is that in power they are integral. I mean, they are integers, they are whole numbers. So f of x equals 3x raised to power 5 minus 5x raised to power 4 plus x cubed plus 6x squared plus 2x plus 7 is a very good example. And that is the plot right there. That's the plot right there. Okay. So you're going to come across functions like this a lot. Then afterwards, we can talk about rational functions. I talked about rational numbers the other time. I tell you that rational numbers, the key word is the ratio you find in that. So a rational number is a number that is a ratio of two integers. But when we talk about rational functions, a rational function is a quotient of ratio f of x, which is p over x over q over x, where p of x and qx are polynomials and q of x is not equal to 0. So what we are saying is that when you put a polynomial over another polynomial, you get a rational function. Of course, you have to ensure that q of x here is not equal to 0, because if that happens, then the function will be undefined. The function will be undefined. So here you have f of x equals 3x plus 7. This is a polynomial. This is another polynomial. Put them over themselves, it becomes a rational function. So the graph of this polynomial now is this is what you see here. Like it has many curves depending on the region you're talking about, because there are jumps. Like you can see that there's a jump around this -5 now, and there's a jump around 0 also. Those are like what you can call, is it, I think asymptotes like that. Okay, so then we go to exponential functions. Exponential functions. So functions of the form f of x, which is equal to a raised power x, where the base a greater than 0 is a positive constant and a is not equal to 0, are called exponential functions. An exponential function never assumes the value of 0. So exponential functions will never become 0. Like you can see from the graph, right? It's the value of y is always positive. Even if you put negative values for x, you always get a positive value of y. And that's why you see everything always above the x-axis, never below the x-axis. So it never gets to 0. It can get very close, but never there. So here we say f of x is equal to a raised power x. This is a typical exponential function. But this a is greater than 0, 1, and then it is never 1. So it means if you start from 2 upwards, so you say 2 raised power x exponential, 3 raised power x exponential, and so on and so forth. And that is why very good examples of exponential will be f of x equals 10 raised power x, f of x equals e raised power x. By the way, that e is actually 2.718, like that. So it's a special number in mathematics. And then you have f of x equals x raised power x. So these are examples of exponential functions. So now if you look at this graph plotted now, so the graph of f of x equals 2 raised power x. You see 2 raised power x is the red line. The red line is 2 raised power x. The green line is, the blue line is e raised power x. The blue line is 2 raised power x, this blue line. Then you have the green line, which is the red is 2 raised power x. The blue line is e raised power x. The green line is 10 raised power x. This is 10 raised power x. And f of x equals x raised power x is the purple line. So this purple line now is x raised to power x, like that. So that is about exponential function. So you have a number raised to the variable, and that becomes your exponential function. Okay, so let's see another type of function we might have in 11. Let's go to slide 11. So this is slide 11. So after the inverses of exponential functions are actually logarithmic functions, as you're going to see. So the logarithmic function y equals log x to base a, with base a as the inverse of where base a is the inverse of the base. What is happening? The logarithmic function, right? Y equals log x to base a, with base a is the inverse of the base a exponential function, y equals a raised power x. Now, of course, just like I said before, you have y equals a raised power x, that's the exponential function. But if you take the log of both, if you take the log of both sides, right, then you get something like log y. If you take log y to base a, that's actually like your x, like this. But of course, this is like the inverse of the log, so that y now becomes log x to base a. And that's what you have right here. So exponent is the inverse of log, right? So The logarithmic function y equals log x to base a with base a is the inverse with the base is a, right? It is actually the inverse of the base a exponential function, which we just talked about previously. And you already know a is not greater than 0, is greater than 0, and a is not 1, like that. So there are two main types of logarithm, namely the natural or Napierian logarithm. We'll come across this a lot. So we have ln x, which is actually log x to base e. So that's a natural or Napierian logarithm named after John Napier. I guess it was the guy that did the four-figure table or something like that. Okay, then you have the common logarithm, that is log to base 10. So you are going to come across this kind of logs a lot. Ln x, that is log to base e of x, and then you're going to come across log x. So if you just have ln x, you know that's log to base e. Or log x, that's a common log. If the base is not given and it's just log, then you know it's base 10. That's a common logarithm. So very good examples of exponential functions will be this. F of x equals ln 4x plus 1, or and f of x equals log 3x. So this simply means log base e 4x plus 1, and this means log base 10 3x, like that. So that's a logarithmic function. Logarithmic function. So exponential function is the inverse of logarithmic function, and logarithmic function is the inverse of exponential function. Okay, so let's see. So these are some examples of logarithmic functions, right? You have the graphs of f of x, that's log x to base 2. That is the red line. So the red line is log x to base 2. And the blue line, this blue line is log x, is ln x, right? That's log x to base e. That's the blue line. And the green line is log x to base 10, the common logarithm, like that. So you can see that all this looks like some kind of saturation. So you have something rising and then saturating at some point. So now all these functions are actually representing realities. So if you want to model things like chemical reactions that reach saturation and all that, you can actually use this kind of functions to represent them. That's why you see that in chemistry, they use a lot of logarithm, because it represents saturation. Okay, so that's some examples of logarithmic equations. So let's talk about trigonometric functions, trigonometric functions. So trigonometric functions involve the 6 trigonometric ratios, namely sine, cosine, tangent, cosecant, secant, and cotangent. And examples are f of x equals sine x, f of x equals sec x minus sine x, f of x equals 1 plus cos x. These are examples of trigonometric functions. They are basically based on sine, cosine, tangent, cosecant, secant, and cotangent. Of course, you know that 1 over sine is what gives cosecant. 1 over cos is what gives secant, and 1 over tan is what gives cotangent. So when you see all that, that's what it is. So you can say cosecant, secant, and cotangent, they are reciprocals of sine, cosine, and tangent. In one of the fast math solutions videos I made, I was talking about reciprocal and inverse. So you're going to see that a lot around here. So if you're able to know the difference between the reciprocal, cosecant, secant, and cotangent are reciprocals of sine, cosine, and tangent. So very soon you're going to see inverses of functions. Okay. So the graph in this figure 5, now you see the graphs of sine x. Sine x passes through the origin and it goes like a wave like that. So the red line is sine x, especially because it passes through the origin. But the blue line is the cos, because it doesn't pass through the origin. It goes at 1 because cos 0 is 1, so it is at 1 at when y and x at the origin, right? It goes up like that. And tangent, tangent is one funny thing. It never, so at tan 90, for instance, is undefined. So once the angle gets to 90 degrees, there's a jump. So that's why you have, for tangent, you have that jump always going like that. So because when it gets to, at 90 degrees, it doesn't, so the function doesn't ever reach anything at 90 degrees. So there's a jump. So it goes again, gets close to that, and it jumps like that. All right. So that's about trigonometric functions. Then we also have inverse trig. Yeah. I just told you about reciprocals now. So talking about inverse trig now, don't ever confuse arc sine of x. Arc sine of x is not the same thing as cosecant of x. Very important to note that. Cosecant is 1 over sine, but arcsine is inverse of sine. So, and their treatments are different. So, especially when it comes to differentiating them, the treatments are actually different. So, inverse trigonometric functions, this involve the inverse of trigonometric ratios as functions that involve the inverse of trigonometric ratios are referred to as inverse trigonometric functions. It should be noted that inverse trigonometric ratios are not the same as the reciprocals of trigonometric ratios, like cosecant, secant, and cotangent, you know. So, in the same way, you should know that arcsine of x is not the same thing as sine x inverse, which is the same thing as 1 over sine x, which can now be cosec. So just leave this as inverse of sine x and treat it that way, so you don't get into any kind of confusion. Okay, so look at the very good examples: arc sine of x, arc cos of x, arc tan of x. These are the inverses of those respective trigonometric functions. So, and you see the graph of arc sine x, you see it's a very interesting graph. It's this small thing in red like this. And you can now see that cosine is like balancing it out. So the inverse of cosine x is like this. And then the inverse of tan x looks like another saturation function. So if you also want, this is another saturation function, like something like a sigmoid function, that, you know, it's a function that saturates, starts from a base, and then it rises, and then it also balances out at that point. So now you need to understand these functions in case in your field, maybe you need to model certain things using certain concepts. So once you know the idea you're representing, you can know the right function for it. So again, we talk about hyperbolic functions. Of course, in literature, for instance, hyperbole is exaggeration. So interestingly, hyperbolic functions, they really look exaggerated. So they get very wide very fast. Like things blow up there very fast. So talking about hyperbolic functions, now they are formed by performing mathematical operations on the two exponential functions. So you have e raised power x and e raised power minus x. So different combinations of these two give us hyperbolic functions. So hyperbolic functions simplify many mathematical expressions and occur frequently in engineering problems. The hyperbolic sine, hyperbolic cosine, and hyperbolic tangent functions are defined by this equation. So hyperbolic sine is something you can call sine. It has an h attached, not just sine. So you now have an h attached. So sine x is actually e raised power x minus e raised power minus x divided by 2. That is sine x. Cos x is now e raised power x plus e raised power minus x divided by 2. And tan x is e raised power x minus e raised power minus x divided by e raised power x plus e raised power minus x. Of course, you already know, if you did a trigonometry, you know that tan is equal to sine over cos. So, and the same happens here, that tan is sine over cos, you know. That means you have e raised power x minus e raised power minus x divided by 2 divided by cos. That is times 2 over e raised power x plus e raised power minus x. And that is why 2 cancels out, and that's why you have e raised power x minus e raised power minus x divided by e raised power x plus e raised power minus x. So that's how that is arrived at. So, and that's what it is to talk about hyperbolic functions. So let's look at the graph. See the graph of hyperbolic functions in slide 16. Now this is slide 16. Okay, so you see that starting from 0, things blow up very fast. Look at the red graph. This red one is sine x, so it just passes through the origin as usual and goes like that. And cos x is the blue line. This is cos x, something like a bowl like that. And then you have tan x, which is also close to the inverse tan of x that we saw the other time. So interestingly, you can see that some of these functions can become some kind of work of art. Okay, so that is hyperbolic function. So let's talk about transcendental function. Interestingly, transcendental function is more like a general, these are functions that are not algebraic. Now, the only algebraic function we have seen is actually that polynomial function. But any other function we have seen so far, they are said to be transcendental. So they include the trigonometric, inverse trigonometric, exponential, and logarithmic functions, and many other functions as well. So they are not polynomial functions per se. I mean, they are not, in fact. But the thing is that there are now rules, like you have things like Taylor's theorem, you have Maclaurin series, with which you can now expand transcendental functions to look like polynomial functions, you know. So a particular example of a transcendental function is a catenary. Its graph has the shape of a cable like a telephone line or electric cable, strung from one support to another and hanging freely under its own weight, as you're going to see here. So these are very good examples of transcendental functions. So you have something like a cable, hanging between two parts. So this is a good example. So for instance, you have 2 cos x over 2, which is the red line. So something like a line suspended, and then you have f of x, which is cos 2x divided by 2. It's also another transcendental function. So that one has not as wide as cos x over 2 cos x over 2. Okay, so then we go to talk about periodic functions. So of course, you know what a period is. It's something that happens over from time to time, is said to be periodic. But I mean, in the mathematical sense, look at what this is. A function f of x is said to be periodic if f of x equals x, f of x plus L. That means that after every L, the function comes back to the same thing, where L is the period of the function. Okay, for a very good example of a periodic event, like of course in the Nigerian context, right? Christmas, maybe some people go to their village every Christmas, right? So, that's a periodic event. So that means that the L here is like can now be said to be 12 months. So after every 12 months, you go back to the village. So that's the idea. So where L is the period of the function. So example is, you see, sine x degrees. After every 180 degrees, sine x becomes the same again. So that's why you see, it goes to 0. After 180 degrees, it comes back to 0. After another 180 degrees, it comes back to 0, like that. So so in this case, you can say that the period of sine is 180 degrees. It's 2 pi. Sorry, it's a pi, right? 2 pi is 360 degrees, so pi. So sine is the period is pi. Then of course for cos, it comes back to the same thing after every 360 degrees. That's for cosine. Okay, so that's a periodic function. Then we have this beautiful thing. In fact, you see some logos that have this kind of thing. So you can see how beautiful maths can be even in influencing brands. So this is actually a very good example of a parametric function. So a function is parametric if both independent and dependent variables are expressed in terms of other variables known as parameters. Example, so you see, normally y is dependent on x, but interestingly, each of those variables, x is now dependent on either t. Each of them is now dependent on t. So you have normally y depends on x, but x depends on t, and y also depends on t. So you can now put them together if you needed to do something. And this is the beautiful plot of this of this parametric function. Sorry. So this is graph of f xy x comma, which is 7 cos 3t. So the x now is 7 cos 3t minus 4, and the y is 7 sine 70 plus 2. And of course, t is between 0 to 2 pi, between 0 and 360 degrees. Okay, so that's a very good example of a parametric function. So what I've been doing so far is just to introduce you to the whole idea of functions, because when we talk about calculus, right, we'll be doing whatever we'll be doing will be based on these functions. So you need to know the different types of functions we have. So let's talk about odd and even functions. An odd function, f of x, is a function such that f of minus x is equal to minus f of x. Now, what does this mean? Okay, we have examples. So f of x equals sine x and f of x equals x cubed. So you know that if f of x equals x cubed, right? By the time you put 2, f of 2 will be 2 raised to power 3, and the answer is 8. But what if you put f of minus 2? That will be minus 2 raised to power 3, and the answer is minus 8. So you see here that f of minus 2 is equal to minus f of 2. That is what an odd function is. But an even function like f of x equals x squared. So if you put 2, f of 2 is 2 raised to power 2, and you have 4. So if we put f of minus 2, you have the same thing. So that's minus 2 raised to power 4. Raised to power 2, and the answer is still 4. So for an odd function, f of minus 2 is minus f of 2. But for an even function, f of minus 2 is the same as f of 2, So sine is a very good example of an odd function because sine 60 and sine minus 60 is okay, we know that sine 30, right, is 0.5. No, sine 30 degrees is 0.5. And we know that sine minus 30 degrees is minus 0.5. But when you come to cos, right, you know that cos 60 degrees is 0.5. But cos minus 60 degrees is exactly the same, 0.5. So whether if you put negative or positive and you get the same answer, that is what the function is even. But if you put negative and positive and the negative one carries minus out, I mean, it produces a minus in the result, then that is an odd function. So these kind of functions do exist. Okay, so let's also talk about explicit and implicit functions. Okay, in fact, any function, most of the functions we have been seeing so far are explicit because an explicit function is a function whose dependent variable can be expressed entirely in terms of the independent variable. All the previous examples of functions given are explicit. So anywhere you can write y is equal to something something, and there's no y again in this in the right hand side, and that is an explicit function. For instance, if you have here y equals x squared plus root x minus 2. This is explicit because y, you don't have y here again. Although this one, it looks like you have y somewhere, but it looks like x cubed and y squared are joined together. But you can still, as far as you can make y the subject, like if you want to make y the subject here, that would be x cubed y squared equals 3 plus 7x, or 7x plus 3 if you like. Carry the 7x here. So you can say this is y squared equals 7x plus 3 all over x cubed. And then finally, your y can be square roots of 7x plus 3 over x cubed. So if you can write y such that there's no y again on the right-hand side, then the function is explicit. But if you look at the implicit case, an implicit function is a function whose dependent variable cannot be expressed entirely in terms of the independent variable. That means you have x squared. So in this case now, try hard as you may, you will never be able to say y is equal to something that doesn't involve y. Then same for this. This is also implicit because try very hard. You cannot say y is equal to something that does not contain y. So that's the difference between explicit and implicit functions. Okay. So let's see some examples of implicit functions. So you have, look at graphs of x squared plus y squared minus xy equals 2x plus y. So the red one, see, it's this thing that looks like an ellipse. And then x cubed minus y squared minus 7xy equals 3x. That's, it has many asymptotes like that. So those are very good examples of implicit functions. So, I mean, at this point, I'll stop. I'll make the second part into another video so that everything does not get too long. So see you in the next video. If you have not subscribed to the channel, please subscribe so you can follow the calculus course and other videos that have been recorded and the ones that will come afterwards. And don't forget to click on the notification bell so you can also get notified when a new video is released. See you in the next video. Thank you so much for listening.